Welcome to Study Recognize Tech Tutorials. In today's session, we will be exploring one of the most essential topics in C programming, arrays. Whether you are a beginner or someone brushing up on core concepts, understanding arrays is a must. Arrays allows us to store multiple values of the same type in a single variable, which makes managing data far more efficient than declaring multiple variables individually. Think of an array like a row of lockers where each locker holds a value and each one is labeled with a number starting from 0. Instead of creating separate variables for 10 student marks, we can create a single array named marks and store all values there. This not only simplifies our code but also makes it scalable and easier to maintain. In this presentation, we will cover both one-dimensional and two-dimensional arrays. You will learn how to declare and initialize arrays, access elements, traverse through arrays using loops, and perform common operations like sum, search, and modification. We will also look into real-life examples such as handling student scores and matrix inputs to better understand the practical use of arrays. By the end of this tutorial, you should be able to write clean and efficient C programs using arrays. Understanding this topic thoroughly will also help you when you move on to more complex data structures like strings, linked lists, stacks, and queues. So stay with us till the end for a complete hands-on experience with arrays in C. Let's begin our journey into the structured and powerful world of arrays. Before deep diving into concepts, let's take a quick look at what we aim to achieve through this presentation. Setting clear objectives at the beginning help us stay focused and ensures that we make the most of our learning time. Our main objective today is to build a strong understanding of arrays in C programming, one of the most commonly used and powerful features in the language. First, you will understand what arrays are and why they are so useful. We will explain their structure, how they store data, and how they simplify working with large sets of similar data. Now, we will move on to how to declare arrays properly. This includes understanding the syntax, data types involved, and the difference between one-dimensional and two-dimensional arrays. Following that, we will learn to initialize arrays in multiple ways. You will get to see how to set initial values at the time of declaration, and how to partially initialize arrays. Understanding these techniques will help avoid bugs and ensure that your arrays works exactly as intended. Then we will explore how to perform basic operations with arrays. These include accessing specific elements, traversing arrays using loops, modifying values, and performing common tasks like calculating sums and searching for elements. We will also highlight some common mistakes beginners make when working with arrays, such as using uninitialized arrays or going out of bounds, and how to avoid them. Finally, you will learn how arrays interact with functions, which is vital for writing modular and reusable code. By the end of this presentation, you will not only understand how to use arrays but also be able to apply them effectively in solving real-world problems. So let's get started and dive into the fascinating world of arrays in C. Let us now understand of what an array actually is. In simple terms, an array is a fixed size collection of elements, all of which are the same data type. These elements are stored in contiguous memory locations, meaning one after another in memory. This organization makes accessing any element by its index extremely fast, which is a major benefit of using arrays. You can think of an array as a row of boxes, where each box can hold one value. Each box has a label called an index starting from 0. So if you have an array of size 5, it can store 5 elements and their indices will range from 0 to 4. This fixed structure is what gives arrays both their strength and their limitation. In C, arrays can hold any data type such as integers, floats, characters, or even user-defined data types. They are especially useful when you want to store a collection of similar items and need to perform repetitive operations on them, such as calculating a total or searching for a value. Arrays are static, which means their size must be defined at the time of declaration and cannot be changed during runtime. This makes them less flexible compared to dynamic data structures. But for many use cases, arrays offer the best combination of simplicity, speed, and predictability. To summarize, an array is a powerful tool that enables you to group data and perform efficient operations on that group. It helps keep your code organized and allows for cleaner loops and algorithms. Understanding arrays is a stepping stone toward mastering data structures and algorithms. So it's important to grasp this concept thoroughly before moving forward. Why use arrays? Now that we understand what an array is the next logical question is why should we use arrays? The answer lies in their efficiency and convenience. Arrays allows us to store a large number of values using a single variable name. This dramatically reduces the complexity of our code and makes it easier to manage, especially when dealing with large data sets. Imagine a situation where you want to store the marks of 50 students. Without arrays, you would need to create 50 separate variables like mark 1, mark 2 and so on. This approach is not only inefficient but also extremely difficult to maintain and prone to errors. With arrays, you can simply declare one array such as mark 50 and use indexing to access or update each student's marks. Arrays are especially powerful when combined with loops. Instead of writing repetitive code, you can use a loop to iterate over each element in the array. This makes tasks like summing all elements, finding a maximum or minimum value, or searching for a specific item much simpler and cleaner. They are also helpful in scenarios where you want to pass a collection of values to functions. Rather than passing multiple arguments, you can pass the array and its size. This makes your functions reusable and your code modular. In short, arrays bring structure to your programs. They allow you to handle data in a more systematic way, provide fast access to elements, and simplify your logic. These qualities makes arrays one of the most essential tools in any programmer's toolkit. Whether you are working on a small application or a complex software project, understanding and using arrays effectively can greatly enhance the quality and performance of your code. Now that we know why arrays are useful, let's look at how to declare them in C. Declaring a one-dimensional array is quite straightforward. The syntax is data type array name of size. For example, if you want to store 10 integers, you can write int marks of 10. This line tells the compiler to create a space in memory that can hold 10 integers, all accessible through the array name marks using indices. The square brackets are used to specify the number of elements the array will hold. Remember that array indices in C start from 0. So an array of size 10 will have indices from 0 to 9. You can also declare arrays of other data types like float, char, or even double. One thing to keep in mind is that once an array is declared with a certain size, its size cannot be changed. It's fixed for the rest of the program. Declaring arrays properly is the first step towards using them efficiently. In the next slide, we will see how to initialize these arrays and give them some meaningful values right from the beginning. After declaring a one-dimensional array, the next step is to initialize it with values. Initialization means assigning specific values to each index in the array. In C, you can initialize an array at the time of declaration using curly braces. For example, int nums of 5 equal to 1, 2, 3, 4, 5. Creates an array of size 5 with the values 1 to 5. We can also do partial initialization. If you write int nums of 5 equal to 10, 20, the first two elements will be set to 10 and 20, while the remaining elements will be automatically initialized to 0. If you omit the size like int nums equal to 1, 2, 3, the compiler will count the elements and allocate the array accordingly. Initialization is important because accessing uninitialized array elements can lead to unexpected behavior. Proper initialization not only prevents bugs but also ensures that your program runs predictably. In the next slide, we will learn how to access individual elements of an array using their indices. Once an array is declared and initialized, accessing individual elements becomes simple. In C, you can access an element by referring to its index using the array name followed by the index in square brackets. It's important to remember that indexing starts from 0. So the first element is at index 0, the second at index 1, and so on. Trying to access an index that doesn't exist, such as a of 3. In this case, can lead to undefined behavior which might crash your program or produce unexpected results. Accessing elements using indices allows you to use loops effectively. For instance, you can traverse the entire array using a loop and perform operations like printing, summing, or modifying values. Accessing elements by index is one of the most powerful aspects of using arrays in programming, and it forms the basis for more complex logic and algorithms. Traversing a one-dimensional array means going through each element in the array one by one. This is typically done using a for loop. You can access each element and perform any required operation. Inside the loop, you might want to print each element using printf or perform calculations such as summing the values. Traversing arrays is essential for tasks like searching, sorting, and performing aggregate operations. The index variable in the loop serves as a pointer to the current element being accessed. Efficient traversal ensures that every element is used or evaluated as needed, and it also helps in debugging or validating the data stored in the array. Understanding how to properly traverse an array is a fundamental programming skill and is key to mastering arrays and more complex data structures. Calculating the sum of all elements in an array is a very common operation, and it beautifully demonstrates the power of array traversal. To do this, you will typically initialize a variable, let's say sum to 0. Then you will use a for loop to iterate through each element of the array. Inside the loop, you add the value of the current array element to your sum variable. For example, int sum equal to 0. This code snippet effectively adds a of 0, then a of 1, and so on until it has added all elements in the array to sum. The visual representation perfectly illustrates this process. Starting with sum equal to 0, it adds array of 0, 10 and making sum 10, then array of 1, 20, making sum 30, and so on until the final sum of 100 is reached. This technique can be adapted for various aggregate calculations such as finding the average, minimum or maximum element in an array. Searching for a specific element within an array is another fundamental operation. One of the simplest methods is called as linear search. In a linear search, you iterate through the array element by element, comparing each element to the value you are looking for, often called the key. As you can see in the example code, for int I equal to 0, I less than 5, I plus plus. If a of I equal to key, break. If a match is found, you can then perform an action like printing the index where the element was found, or in this case, break out of the loop because you have found your target. This visual clearly depicts this process. The search starts from the beginning of the list, checking each number sequentially until the key, which is 3 in this example, is found. While linear search is straightforward to implement, it can be less efficient for very large arrays. However, it's a great starting point for understanding such algorithms. Not only can you access and read array elements, but you can also modify them. Modifying an array element means changing the value stored at a particular index. This also typically done using a for loop, especially if you want to apply a change to multiple elements or elements. For instance, the code for int I equal to 0, I less than 5, I plus plus, a of I equal to 2 will iterate through the array A and multiply each element's value by 2, effectively updating the array in place. The image on the right, while showing printf examples, also highlights the direct access and modification capabilities of arrays. You can directly assign a new value to an element using its index, like array of 0 equal to new value. This ability to easily update elements is essential for many programming tasks such as sorting, filtering, or processing data based on certain conditions. Always ensure that when modifying elements, you stay within the valid index range to prevent errors. To make your programs interactive and dynamic, you often need to get input for array elements directly from the user. In C, you can achieve this using the scanf function within a loop. The example demonstrates how to read integer values from the user and store them into the marks array. The AND operator before marks of I is crucial. It provides the memory address of the array element which scanf needs to store the input value. The terminal output you see visually confirms this process. The program prompts the user to enter a list of integers, and as the user types numbers like 4, 9, 7 and 6, these values are stored sequentially in the array. This method allows you to create a flexible programs that can handle varying amounts of data or data provided by the user at runtime, making your applications much more versatile. So far we have focused on one-dimensional arrays, which are essentially lists of elements. But what if your data has more tabular structure like a spreadsheet or a grid? That's where two-dimensional arrays comes in. Two-dimensional arrays often referred to as matrices or tables or are arrays of arrays. They have two indices, one for the row and one for the column. Think of it like a grid where each cell holds a piece of data. The syntax for declaring a two-dimensional array is given. For instance, declaring a 2D array named matrix with 2 rows and 3 columns capable of storing integer values. This visual clearly illustrates how a 2D array is organized with rows and columns. Understanding this structure is key to working with data that has multiple dimensions such as image pixels, game boards or mathematical matrices. Just like with one-dimensional arrays, you can declare and initialize two-dimensional arrays. When initializing a 2D array, you use nested curly braces. The outer set of curly braces encloses all the elements of the array, and each inner set of curly braces represents a row. For example, declares a 2 by 3 integer matrix. The first inner set 1 comma 2 comma 3 initializes the first row 0, and 4 comma 5 comma 6 initializes the second row 1. Each element within a row is then assigned to its respective column. The image vividly contrasts a 1D array as a single row of elements with a 2D array as a grid. This nested structure for initializing makes sense because a 2D array is essentially an array where each element is itself another array, a row. This method provides a clear and organized way to set up your multi-dimensional data structure from the outset. Accessing elements in a two-dimensional array is similar to 1D arrays, but now you need to specify both the row index and the column index. The general syntax is array name of row index, column index. Remember that both row and column indices also start from 0. So to access the element at the second row and third column of a 2D array named math, you would use math 1 2. Why use 1 2 and not 2 3? Because 1 refers to the second row since rows start at index 0, and 2 refers to the third column since column also start at index 0. In the example, printf would print the value 6 if math was initialized as 1 comma 2 comma 3 comma 4 comma 5 comma 6. The visual reinforces this by showing array of 1 0. Pointing to the element 4 in a sample 2D array. Understanding this double indexing is crucial for pinpointing and manipulating specific data points within your tabular data structures. Traversing a two-dimensional array means visiting every element in the grid. Since a 2D array has both rows and columns, you need two loops to accomplish this. In a nested loop structure, typically the outer loop iterates through the rows and the inner loop iterates through the columns of the current row. As shown in the code example, this ensures that every element is visited exactly once. This pattern is essential for any operation that requires processing all elements in a 2D array, such as printing the entire matrix, performing calculations on each element, or searching for a specific value across the entire grid. The output illustration clearly shows how a nested loop would print the elements of a gradebook matrix, iterating row by row and then column by column within each row. Just like with one-dimensional arrays, you can calculate the sum of all elements in a two-dimensional array. This operation also leverages the power of nested loops. You will typically initialize some variable to 0, then use an outer for loop to iterate through each row and then inner for loop to iterate through each column within that row. Inside the innermost part of the loops, you add the value of the current element to your sum variable. The output on the screen illustrates a program taking input for a 3 by 3 matrix and displaying a sum. This approach ensures that every single element in the 2D array contributes to the total sum. This principle can be extended to other aggregate operations such as finding the average, maximum or minimum element across the entire two-dimensional array, making nested loops indispensable for 2D array manipulation. Searching for a specific value within a two-dimensional array also requires the use of nested loops. Similar to a linear search in a 1D array, you will iterate through each row using an outer loop and then through each column within that row using an inner loop. Inside the inner loop, you compare the current array element to the key you are searching for. If a match is found, you can then typically report the location, row and column indices or perform another action. The example output demonstrates this beautifully. It shows a list of names stored in a 2D array. When the user searches for Roshan, the program correctly identifies that Roshan found at position 3. While this example is for names, the underlying logic of using nested loops for systematically check every element applies universally to any data type stored in a 2D array. For larger arrays, more advanced search algorithms might be considered, but for general purposes, nested linear search is effective. Handling input and output for matrices or two-dimensional arrays consistently relies on nested loops. To read values into a matrix from a user or a file, you will use nested scanf or file input functions within your loops, ensuring that each row and column is populated correctly. Conversely, to display the contents of a matrix, you will use nested printf statements. The outer loop controls the rows and the inner loop controls the columns. Within the inner loop, you would typically print the element, often followed by a space, and then after the inner loop finishes, you would print a new line character to move to the next row for a formatted output. The provided C code snippet, while focused on calculating a column sum, visually reinforces the concept of using nested loops and to process elements in a 2D array, whether for input, output or calculation. Arrays are incredibly practical, and a common application is managing student scores. You can use a one-dimensional array to store the scores of multiple students and then easily compute their total and average scores using the traversal and summation techniques we have discussed. However, as powerful as arrays are, there are some common mistakes to watch out for. First, always avoid using uninitialized arrays. If you declare array but don't assign initial values, its element will contain garbage values, leading to unpredictable program behavior. Second, critically important, avoid index out of bound errors. This happens when you try to access an element using an index that is outside the valid range 0 to size -1. This is a frequent source of bugs and crashes. Finally, when working with arrays and functions, remember that you can pass arrays to functions. The syntax shows that how you would declare a function to receive an integer array and its size. This allows you to write modular and reusable code, separating concerns and making your program more organized. Let's summarize the key advantages of using arrays, highlighting why they are such a staple in C programming. Firstly, arrays offer efficient access to elements due to their contiguous memory allocation. This means elements are stored right next to each other, allowing for very fast retrieval using direct indexing. They support homogeneous data, meaning all elements are of the same data type, which simplifies memory management and data processing. Arrays also lead to simplified code and structure by allowing you to manage large data sets under a single variable name, reducing the need for numerous individual variable declarations. The direct access by index capability enables random access to any element, which is incredibly useful for various operations. Furthermore, arrays provide ease of iteration and enable simplified algorithms for tasks like sorting, searching, and calculations. Finally, they offer memory efficiency for fixed sizes and robust support for multi-dimensional structures, making them versatile for complex data representations. These advantages collectively make arrays a highly efficient and effective data structure for many programming scenarios. While arrays offer numerous advantages, it's equally important to be aware of their limitations, especially with simple arrays in C. The first and most significant limitations is their fixed size. Once you declare an array with a specific size, you cannot dynamically change that size during program execution. If you need to store the more elements than the declared size, you will run into issues. This also means there is no built-in resizing mechanism. Another critical limitation is the lack of bounds checking. C does not automatically prevent you from accessing an index outside the array's declared range, leading to array out of bounds access, which can result in undefined behavior, crashes, or security vulnerabilities. It can also be hard to get the current size of an array if you have only passed a pointer to its first element to a function. And as we discussed, uninitialized arrays can lead to garbage values. These limitations are largely due to C's focus on efficiency and backward compatibility. However, later in your programming journey, you will learn about other data structures like dynamic arrays or std vector in C++, which addresses many of these issues. Alright, we have covered a lot of ground today. To quickly recap, we started by understanding that arrays are fixed size collections of elements of the same data type stored in contiguous memory. We then explored how to declare and initialize both one-dimensional and two-dimensional arrays, emphasizing the importance of indexing starting from 0. We delved into fundamental array operations including traversing arrays and using loops, calculating the sum of array elements, and performing linear searches. We also touched upon modifying array elements and taking array performing linear searches. For 2D arrays, we learned how to access elements using doable indices and applied nested loops for traversal, summation, and searching. Remember the common mistakes to avoid, like out of bounds access and using uninitialized arrays. Finally, we reviewed the advantages and limitations of arrays. Now it's your turn. Encourage you to try out some practice problems related to arrays to solidify your understanding. And of course, if you have any questions, feel free to leave them in the comment section below. Thank you for watching, and don't forget to like, share and subscribe to Study Recognize Tech Tutorials for more programming insights.